extrasolar planets, or exoplanets, has really caused us to question our own place in the cosmos. And the studies of the solar system, which have gone, I feel like have gone from, oh, that's something that everybody knows about, and we know everything that there is to know about the solar system. We've gone from that attitude to thinking that maybe that isn't the case. And people now are very interested in studying the dynamics of solar systems, not only our own, but also others. So thank you. Plenty of time for questions if anyone has any. Yeah,
is the gravitational pull on the mass gaseous planets greater or less than a rock planet against toward their moons? Sort of to the moons.
To the moons?
Yeah. So in other words, I'm sorry. Is the gravitational pull, say, like the rock planets to the moon that circulate, go around and circulate the rock planets? Is there a difference between that and the gas planets?
Yeah, there will be, because if you think about like the moon going around the Earth, and then the moon's going around Jupiter, the force between the moons around Jupiter is going to be much larger, just because Jupiter is so much larger. And so if they're close, or say that there was a moon at the same distance from Jupiter as Earth's moon is, it would go around a lot faster, because there'd be a larger gravitational pull from Jupiter. Yes?
You know that planet that they found in the Goldilocks range? Is that what you call that?
Yeah.
Did they name that planet? That's the good one?
Yeah, I think it's called Giselle 81b or something,
Okay.
or 581b.
Okay.
So it doesn't have a special name, but
Yeah.
and any planets that are discovered by the Kepler mission are called Kepler 7, or they're up to Kepler 9, I think. And then if they discover more than one planet in a solar system, then they get letters, so B and C. Maybe someday they'll have someplace where you can pay to name your own planet, like they have to pay to name a star, right? If we discover enough of them.
Let's see that picture of the double pedal.
You want to see it? Oh yeah, you want to see
it?
it?
Still running?
Yeah. Let's see what happened with the double pendulum. Let's see. Yeah, so it's looking pretty black. So it's filled in most of the perimeter space now. Yes, please.
Can we interpret it like kind of a probability wave thing where you have a certain probability, a zone CC, it's like a belt. It's not a perfectly shaped like a space filling curve. It's only lands on certain places on this graph. So there must be a certain pattern to its motion. Although the pattern is hard to quantify with a mathematical equation, it does exist, am I right?
Yeah, so that's true, that if I knew the starting position with accuracy, I can always predict where that pendulum will be. But the problem is with actually, if you were to sit down and try to calculate it out, that oftentimes computers don't have that type of precision to be able to do it. And so if I want to integrate the motion of this pendulum over a long period of time, I don't know how long that would be, maybe some hours, that eventually, because of errors, I won't be able to predict exactly where it is. But you're right in that I could think about it in a probabilistic sense, so that I could say, well, I don't know where it's going to be, but it has some probability of being in this position here, with 10% probability or something like that. Yeah, so you could think about the problem in that way as well.
Has any work been done on the number of asteroids that leave the asteroid belt and potentially would cross the paths of the inner planets?
Yeah, so there's a lot of work that's done in that direction. So there are telescopes that observe every night looking for asteroids that are near the Earth, or could be, I guess, in scary orbits. But let's see. And there's a lot of solar system simulations that deal with this exact problem. So, what's the probability that an asteroid will be ejected from the solar system, and what will happen then? This is actually an interesting question, because we think in the early solar system there were a whole bunch more asteroids, a whole bunch of small things called planetesimals that populated the entire solar system. And when the sun turned on, originally they're embedded in this sort of cloud of gas and dust, but when the sun turns on, it sweeps all that gas and dust out, and these planetesimals are exposed, and most of them have been ejected from the solar system. And we think that, so for example, if they cross paths with a large planet like Jupiter, they're for sure going to be ejected from the solar system. So just like we use gravitational flybys to influence the path of a satellite, if one of these flies nearby Jupiter, for example, it could be just completely ejected from the solar system. And by looking at, I guess, statistical properties of how that works, people determined that the giant planets probably have migrated from where their current positions are. So if Jupiter or some other planet ejects a whole bunch of these little planetesimals, so if it ejects them inward, that will cause that planet to migrate outwards. And we actually have evidence that this has happened because, for example, if you look at Neptune, we think it's moved because it's captured a whole bunch of things into orbital resonance with it. So Pluto is in orbital resonance with Neptune, and there are a whole bunch of other objects that are in orbital resonance with it as well. They're called Plutinos, in the same orbital resonance, and Tutinos, in I think twice the orbital resonance of that. And because of this capture and resonance, we believe that can only happen if Neptune moved or swept through those bands of resonance. So there's definite evidence that this ejection process happens. But I guess the scary part about it is if it is chaotic, then it could just happen. And then, we'll just have to keep watching the sky to make sure that we see anything that could be a potential threat. That's the long answer. Okay.
I'm still thinking about that pendulum.
Because it's still up here.
Yes, sure. So if you drag the two balls to the exact same starting position, then do you recreate the exact same pattern of movement?
Yes. If you were to drag them to the exact same starting position, yes. But
and if a slight shift will just completely drop
yep.
it out.
And a slight shift completely destroys it, right? So that's like the Plinko game, that even though these three balls started at nearly the same position, after a short time, they diverge from each other. But yeah, if you knew that if they started exactly the same, of course the motion would be, of the two pendulums would be exactly the same. Anything else? Okay, so thank you.